So this is a take two of the FIPS talk. I was supposed to give exactly this talk last year, but I lost my voice, so even remote sambaXP conference did not help. Yeah, and then I got COVID, and then I got all the consequences of that. So, but I'm here, and I can give a talk, and most of the meat in this presentation was derived by my colleague Julian Risch. Julian is an engineer at Red Hat who maintains MIT Kerberos in Fedora and RHEL. He came to Red Hat from, I think, from CERN, where he was the guy doing the FreeIPA deployment at CERN. So the whole CERN was working on that architecture. And his work on MIT Kerberos proved very fruitful for this work. So the talk will show that. So first I want to start with kind of explanation what this FIPS 140 is. The FIPS 140 is a set of standards. It's security requirements towards the systems deployed in the governmental organizations in US. But in fact, these set of standards, they serve as a basis for security requirements almost everywhere in Western world, and in many commercial organizations, they base their security requirements on the requirements set by the NIST organization. And we had two iterations of this. So FIPS 140-1 was published in how many? 30 years? 1994, almost 30 years ago. Then in 2001, FIPS 140-2 was published. So the span of this standard was like already 22 years. And there are some certifications that's still valid. So until the certification expires, you can use that system in use. But 140-3 supersedes 140-2. It removes some stuff, it adds some other requirements, and so on. And you cannot deploy now that the standard is out, you cannot deploy new systems without this certification. The certification actually applies to crypto modules. It's not applying to the system overall. You have to certify a cryptographic tooling that all other applications in your system use. And then you have to guarantee that everything else is using certified crypto. They cannot roll their own crypto, which is a fun for Samba, or was a fun for a long time, because Samba did have a lot of own crypto. And because in open source we value kind of diversity in the tooling, there are many crypto libraries. And if you're shipping a general operating system, you have to provide most likely most of them, because you have applications that use this or that library, and they all have to be certified. So this is time-consuming, resource-consuming, financially challenging thing, because every single module of those have to be certified. And if you look at the certifications, there's pages which list you existing certificates that are valid, already expired, and so on, and so-called systems under evaluation and test. They almost every single vendor submits their crypto modules for this, because that's part of the business. If you want to go into environments where these things have to be done, you have to follow them. So if you look into RHEL 8, RHEL 8 has 140-2 certificates, multiple of them. And we focus on like 5 big components. These OpenSSL, GNU TLS, NSS, and libgcrypt. These are crypto libraries, right? And then kernel has its own set of crypto primitives and have to be certified as well. And that's interesting task. If in past OpenSSH had its own crypto, libSSH, libres1, which is VPN thing, has to use their own crypto. With RHEL 8, this was changed. They were switched to use one of those libraries, and therefore they don't need to be certified explicitly in this process. Only the crypto modules have to. With RHEL 9, it's a separate cryptographic module, set of modules. There are 5 of them, and the certification process still continues. It started, as you can see, mid-June last year, and it's still ongoing. If you go by this link, you will visit this cryptographic module validation program, and you will see the implementation under test from everyone. So literally, like all RHEL rebuilds, these commercial companies behind them submit their own modules which base it on the same code, and they work on certifying them. Each vendor chooses which library, which laboratory to use to do these certifications. There are certified laboratories. They perform operations on behalf of NIST, and they go back and forth with vendor fixing problems. So this goes back, in best cases, it goes back into the distribution maintainers. They have to fix problems. They can go upstream and submit these upstream things, and so on. So now we have RHEL, Rocky, Alma, Oracle, Canonical with Ubuntu, and I think SUSE as well, and so on. So like 6 or 7 vendors submitting certification requests for all of these things, and then using different laboratories for this, and then coming back with the patches. So it's a sort of a cross-pollination for open source community, which is a great way of participating and getting different views on the security problems and fixing them, and enhancing this for everyone. But the problem is this process takes more than a year usually, and most of this work typically done in the distribution specific branch of that module. They diverge enough so that merging them upstream becomes a problem. And if we look into changes that happened with 140-3, there's literally a bunch of stuff that simply doesn't work anymore. So for example, there's one of the standards, a separate standard that 140-3 refers to, removed DSA algorithm completely. So you cannot use that anymore in the systems that should be compliant with this, which was published just a few months ago. Remember, we submitted our modules last year. So the change happened while we are testing our implementation. We have to apply to these changes and force kind of new changes in the code and distribution and so on. Then FIPS 180-4 is being revised to remove SHA-1 more this later. But the thing that happens is that the guidelines has been set, the modules being certified, and nobody does care from those organizations how this really reflects on the actual world. If you want to be used in the environments where these regulatory things have to be there, you have to comply. How you achieve that compliance in your software, it's up to you. So what happens is that the compliance is a matter between vendor, a customer, and who audits the customer, the FIPS auditor for the customer. This goes into weird situations. For example, this is SHA-1 announcement that was in December last year, that the plan from NIST, we will publish all the updated documents that say SHA-1 has to be deprecated and never used anymore after like 7 years in future, right? In 2030. But this also means that labs get to interpret this statement pretty strongly or differently depending on the lab. The one that Red Hat is using says you cannot use SHA-1 anymore now, not in 2030. So you have to change your code to disable SHA-1 by default. You cannot use some custom parameters. We love custom parameters, but no. Only well-known curves can be used to instantiate parameters to different crypto, which in turn means if your library provides a way to instantiate custom things, they must be disabled in the certified module. That means maybe there is an API that must be completely removed or changed implementation that prevents non-well-known curves and this back and forth. This takes months to communicate, back and forth changes, the guidance updates as regulations being developed, and it's fun. It's truly fun to get through this. So in the reality, if you look at this at the face value, what is now, you cannot run Active Directory or integrate with Active Directory with FIPS 140-3 for multiple reasons. I'm mentioning here just two of them, which basically kill down the whole story. I should have probably made a slide, a presentation with one slide that says, well, game over, like Andreas had in his presentation. And we happily can spend this time on joking. The reality is Microsoft has submitted their implementation under test for all components of Windows April 14th this year. So maybe, given that it takes a long time, maybe next year or something, we will hear something from them, because there's nothing. And current implementations of the Microsoft protocols do not really enable use of crypto that is allowed. So what is not allowed is AS1 ciphers that use SHA-1 as the HMAC. SHA-1 HMAC is allowed, but the way how it's used in Kerberos basically makes the KDF function not usable for the FIPS 140-3. The other part is that SHA-1 hashes used in PKINIT implementation in Kerberos. While Active Directory supports elliptic curves, MIT Kerberos does not support elliptic curves for PKINIT. And when there's the other side doesn't support elliptic curves, you cannot use elliptic curves. Windows systems always fall back to SHA-1. So if you want working systems, you will have to support SHA-1, and there's no SHA-1. Luckily, what happens is, as I said, this is a matter between vendor, customer, and FIPS auditor. They have to agree to what level of using the software that they have, they can support these regulations. And they have to write this down. And in most cases, this is what happens. Formally, 140-3 is probably not really employed anywhere, because there are no general purpose operating systems that actually have certified crypto components by FIPS 140-3. But there are 140-2 ones already. And how we, from the operating system level, how we control this. If every single application, every single user of these crypto libraries, they have to create configuration files, they have to create something. How you control this centrally? Well, the way how we do this in RHEL and RHEL derivatives for quite a long time now, since I think RHEL 7, so this is more than 10 years now, there is so-called system-wide crypto policy framework. That framework is a set of rules. Initially it was written in Perl, nowadays it's in Python and modular. It allows you to express certain requirements and say that, okay, we have this policy that corresponds to FIPS, which means only these TLS ciphers enabled, only these MAC things enabled, only these hashes allow it for signatures, for verification, and all of these things. And then the crypto policies framework generates configuration files for all frameworks that it supports. So from Active Directory point of view, the most important one is literally Kerberos, not anything else, because, well, TLS, for TLS we do apply default settings, but the most interesting thing happens inside Kerberos. For, like, if you stand up HTTP server, then obviously that would use some SSL or TLS module, and that one will use a crypto library that will import default settings from these things. So this kind of how it looks like in the upstream. There are tests that generate the output files, and they look like this, and internally they contain configuration for each specific type of framework. So for example, Bind, Java, Kirby 5, Libris 1, and they all get their own snippets, and these snippets included into the default configuration. Now, in most cases, patches for enabling crypto policy were rejected by the corresponding upstreams. So these is downstream patches in RHEL and Fedora and RHEL derivatives. I don't know about SUSE, whether SUSE uses the same framework or not. It's but it's useful in the sense that you define it in one place and it's triggering updates everywhere. The system-wide crypto policies allows you to actually switch things more flexible. So there's notion of sub-policies. You can say that, okay, I want something weird like future policy, which is like removing everything that is considered non-working, and then add on top some legacy stuff. Or you can use FIPS, and this is how we provide ability to amend FIPS with AD support. AD support is a sub-policy that enables Kerberos encryption types that Windows supports, but doesn't enable RC4 HMAC, for example. So only AES stuff. So you can have these kind of things. And depending on a distribution version or a distribution as a whole, there may be different default, different subset of policies. So for example, Fedora does not want to disable SHA-1. The community decided there are so many use cases that they want to keep it. So you can set default no SHA-1 in Fedora to emulate default policy from RHEL 9. And the default policy in RHEL 9 for MIT Kerberos generates this kind of config. So you can see that this is AES-256 SHA-1, AES-256 SHA-384, AES-128 SHA-256, and so on. But in FIPS mode, this gets stripped of the types that are not allowed in FIPS. This is just an example. There are more config files generated. These snippets included through the include directories or directly. That's why include directories for the configuration files is generally a good thing. It allows this kind of customization without touching your directory stuff. And then when you have all these defaults, you can trigger compliance for the applications kind of more in a wide way. So one thing I said already is that, okay, libraries patch it to load these defaults. You don't need to manually define this for every single application because defaults apply it universally. What happens is that if non-compliant crypto primitive is called, application will fail because library will fail to use it. That's one way. The other way is when application is smart and basically queries what's supported, you don't simply return unsupported types. So then application chooses the one that it knows, but from the list of what is really supported. And many applications behave properly here. But really, if there's an application that says, okay, I want RC4, in FIPS mode, you cannot get that. So you cannot do anything. You will fail as an application because you cannot continue. There are a few things how deal with this, but application needs to be modernized if it wants to kind of deal with it. And there are different types of modernization that might apply. And I try to express three big areas because these are like, the more you go there, it's a rabbit hole, you find more and more problems, but looks like most of the problems can be separated in these three broad areas. So defaults for the app modernization. So for example, if you're using FreeIPA is using MIT Kerberos. Kerberos needs a master key to encrypt all the other keys. For the new installations, that's easy. You change the master key on the new installations. You put something there that is compliant and compatible with the strictest policy you have to do. So, okay, AES-256-SHA-2 is nice choice. We change it, new systems will work. Anything that is generated within that will use the defaults, and defaults basically do not permit to use other types that cannot be used, right? If you had some old stuff, then, well, for example, for the user, you had some hashes there, and you tried to change a password, a new password will be generated using only new hashes. So new encryption types. So you will automatically lose the old ones and if you will be in policy. The other part is that when you talk between systems, you need to be prepared that choices you made when you create an application will not be the right choices anymore. So this is called typically algorithm agility, so that when a client and server communicate with each other, they choose what they agree on. If they have a common agreement, they will choose that one. And it also becomes very important because of the post-quantum work. Most of the algorithm and crypto primitives used today, well, there's some agreement that most of it will be broken by use of quantum computers. So algorithm agility is one of the ways to prepare to that, so that choice of specific algorithms is dynamic and not static. And applications, if they prepare for algorithm agility today, they will be ready to switch to a new thing in future. The problem is that applications typically implement some protocols that have some definitions, and these RFCs for these protocols extremely hard to update. The whole process is designed to review, take time, and agree on the things. And sometimes when certain RFCs were written in past and everybody happily moved forward, nobody updates them. Nobody really spends time. So adjusting that and adjusting actual implementation takes years. So that's why announcement, okay, we intend to do SHA-1 deprecation in 2030, today gives us 7 years to prepare for actual enforcement of it. But in reality, all these crypto laboratories will start enforcing it now simply because they know how slowly moves the industry overall. And also we get this problem that there are still old systems. You have to use these old systems until they expire, especially if they still have valid certifications and valid compliance there. So how you make them interoperate with each other, with new systems, how you transition and all this stuff, that's a lot of work. So just one case. I'm not going to look at everything here. Just one case inside Kerberos. It's a PKINIT. So this is extension that allows use smart cards or similar devices to obtain Kerberos tickets. And there is algorithm agility for PKINIT. There is an RFC which says that, yeah, you can do a choice. SHA-1 is not necessarily, you can do SHA-2, SHA-256, SHA-512, and so on. And you supposedly need to implement this in the implementations. And if they do, then they say, okay, I support this, this, and this, and let's agree on something. Then there are other RFCs, and they effectively depend on few crypto primitives and kind of techniques. So one of them is Diffie-Hellman exchange using X942. I think it's a SN1 encoding of the parameters for Diffie-Hellman, where certain groups used for this exchange, they must be supported by the compliant implementations. And there are two groups marked as required. So group 2 and group 14. To cut things short, group 2 is not considered safe for maybe 15 years already, but it's still on the list of recommended for use by different protocols, not just PKINIT. Group 16 is something good that we can use. Then the other part is how you read these RFCs when you do your implementation. So for example, PKINIT RFCs say that digest algorithm and signature algorithm at the top level of package defined, they might be different. But the way how it's stated makes it reading ambiguous. So Heimdall uses often different digest and signature algorithms, but OpenSSL CMS engine that is used by MIT Kerberos to implement PKINIT hard codes that both digest algorithm and signature algorithms are the same. And they do not consider this a bug, they consider this a feature that they don't support it this way. And there's no agreement, so you will fail to parse and interoperate even between two open source implementations. The other part is, while MIT Kerberos implements some of this agility, it's not the full agility part. The other thing is that there's no support for elliptic curves in MIT Kerberos PKINIT. So you cannot forget about the SHA-1 digest or signature algorithm and switch to elliptic curves like Windows does. You cannot interoperate with Windows if SHA-1 is not available. And then Active Directory does not support new modp groups. So it doesn't support group 14 and 16 and even 18, which is the newest one. And that means that we cannot do anything there. There's simply no way to interoperate. And Heimdall defaults to the group 2, which means as soon as this packet reaches you, even if there are other groups available, OpenSSL implementation in MIT Kerberos will fail to parse that packet at all. It cannot even switch to the next one. It will reject everything. So you have to do something with this to avoid it. In the case of FIPS 140-3 certification, we even have more interesting situations. So I say that all vendors submit their own implementation. So Red Hat has own FIPS provider. OpenSSL upstream has its own FIPS provider. It's the same code, but heavily patched in both cases. So they diverged enough that merging these things makes little sense because both organizations use different laboratories to do certification, and they apply different standards to each other. I'm not saying which one more strict, so it's harder to say, because in specific cases they make different point of views. These are organizations that live and breathe with security and crypto details, and they make decisions, and that's how they live. But this means that if we apply on application level, in this case MIT Kerberos, apply decisions based on behavioral one stuff or one library or one provider, we will probably have problems with the other one. So we have to do all of this working together and testing. And now just remember that there is also Rocky Linux, Alma Linux, Oracle, and so on. They have their own submitted versions. Those versions, well, started with RHEL FIPS provider, but they use their own labs and they get their own requests. So at some point they have their own patches on top. It's an interesting story. So this one example that I say that Heimdall defaults to mod P group 2. We cannot decrypt this group. Heimdall provides group 14, but OpenSSL simply fails earlier. Now we consider this OpenSSL failure. OpenSSL considers that this is a feature from their side. So there's still disagreement. They accepted this as a feature request, which means a totally different level of commitment to implement that than a bug in a certified implementation. The other thing is, if you disable SHA-1, you cannot verify Windows PKINIT clients because you cannot do elliptic curves in this implementation. But if you disable SHA-1, the older clients, your own older clients, RHEL 7, RHEL 8, will not work because they don't support this. So we had to backport a lot of stuff into RHEL 8 and RHEL 7 to make support for SHA-2 schemes and so on. The same with the defaults for supported CMS types. So we moved to SHA-256, but Windows does not work with this. So a lot of backporting after the fact, after you already have stuff in the compose and in the distribution. So how we do this? Because in MIT Kerberos we use OpenSSL. OpenSSL 3 has this notion of providers, and you can actually dynamically load different providers. So for different purposes we can switch between providers. For the basic and most important part, we use FIPS, but where we know that FIPS will fail, if we are allowed to use by the system crypto policy for the whole system, if we allow it to use that algorithm, we can load the old one, the default one that has this implementation, and apply crypto primitives for that one. Not in the strict FIPS case, again, but in the cases like FIPS AD support legacy that allows you to apply all of these things. This is needed because from OpenSSL 3.0, a FIPS provider has removed those crypto primitives that are not allowed in FIPS 140-3. So it, for example, it does not have SHA-1 at all. There's no implementation, so you cannot even explicitly call for it because there's no code. You have to use something else. Then the other part. We started this work maybe 4 or 5 years ago as a Samba team, talking with Microsoft people that, hey, we really need to get rid of RC4. We need to get rid of NTLM use. And there's plenty of RPC calls that imply that you have hashes with RC4, imply that you're using session keys built on RC4 and so on. And this simply doesn't work even in FIPS 140-2. So there was a lot of back and forth, often forth we are saying and not hearing anything back, and maybe a year later we're hearing, hey, there's new specification for new LSA or summer calls that uses AES now. So you can use that one for something. And we ended up implementing, mostly Andreas and Günther implemented a bunch of these new variations of these calls. There's another set that came just a few months ago we have to do. These are not using new AES ciphers. They use some of the AES variants that Windows supports now. I hope that when they get certified FIPS 140-3 crypto libraries, they will add more modern stuff. And one of those examples is this create trusted domain relax thing that encapsulates actually all the work needed to establish trust using AES-based cryptography. The reason for this is that you have to use AES-based session, and you have to enforce that this AES-based session was used, and you cannot leak the other cryptographic material outside of the flow of it, and Samba encapsulated all of it. So both Samba tool and FreeIPA call this function if it's available to establish trust instead of generating credentials itself and getting things. This function then enforces that the connection over which trust is established uses session with a session key based on AES, and therefore applies FIPS kind of requirements towards the secured connection, because whatever is in that AES session, AES protected session, is considered a plain text, and we can handle that just nicely. But of course, because this uses cryptography that is strictly speaking not valid for 140-3, it's still not enough there. Now that's runtime. Okay, you work with data. What do you do with data if you have to migrate that data from the older systems? You cannot migrate data from non-FIPS to FIPS. You have to put barriers somewhere. You cannot guarantee that what was generated before FIPS was enforced is safe. So this is an imaginary case. Nobody really does use Samba AD in FIPS environment at this moment. But if we would need to, we would need to do something with the data, right? If it was generated prior to FIPS 140-3. For example, somebody installed Samba AD in 140-2 environment and they need to upgrade. So luckily, yeah, you can get access to the old encrypted keys if you apply an extended policy that does not filter it from the crypto libraries. You can then regenerate keys, Kerberos keys. In Active Directory case, Samba AD stores the plain text of these passwords in encrypted containers that can be then decrypted and password taken and regenerate new keys, and kind of that's possible. So offline regeneration is possible. It's not implemented, but technically possible to do. On the domain member case, because machine account password does exist, you can generate whatever you can. So that's sort of solvable case if you know what to do, but it's a certain amount of work to do, for sure. In IPA case, there's this interesting situation that IPA doesn't have anywhere plain text passwords at all. So yes, you have encrypted keys. If they encrypted with the previous cryptography, you can read them, but that doesn't give you anything. You have to generate new keys completely. So for users, maybe this is a good point when you move passwordless using new other mechanisms. For example, using the smart cards, which does not need to store anything crypto specific on the user account. So you don't have real encrypted Kerberos keys there, you just use your smart card. Or you use FIDO2, which I will be talking tomorrow about. FIDO2 tokens for this. So this is a good point. Or you use something like OAuth to identity provider. Again, no crypto keys, great, because you can migrate without them. But if you have services have keys, and these keys need to be replaced. So one of the rotation on the domain controller side, because each domain controller is kind of isolated, talks to its own, it can rotate keys in one go without much problem. We have this more or less automated. On the client side, the key tab with the machine account effectively needs to be rotated, but you have to prove that you are somebody who has rights to do this. So it's either you're admin and needs to apply admin permissions to do this rotation, or IPA has this mechanism to authenticate with PKINIT, and PKINIT can be flexibly mapped to any account, including the services. So you can use some certificate mapped to this service account to present as if you're a service without the encrypted key, and then regenerate key for yourself. So this is also possible to rotate all of this.